All right, thank you very much for that kind introduction. So my name is Dr. Bramwell, Brizendine, and I'm an assistant professor and the founding director of the Verona Lab. I'm also the creator of the JOP Rocket, which deals with jump-oriented programming, and ROP Rocket, which deals with return-oriented programming, and ShellWasp, which allows us to use Windows API or Windows syscalls in Shellcode, and of course, SHAREM, subject of our talk today. This is an NSA-funded project. I've presented at many different conferences from DEF CON, Black Hat, Hack in the Box, Virus Bulletin, and others. I do a PhD in cyber operations. It's a highly technical degree focused on malware analysis, reverse engineering, and software exploitation. So I'm only one person here today, but there are many others who contributed over the years. So we'd like to give a shout out to our team members, and also to Max Kirsten of Trellix, who did the Ghidra plugin for SHAREM, which we will address. And also this month, in October 2024, we'll have a new group of students who will be working as part of on SHAREM as part of the Viceroy program in the US. So first we can talk about why Shellcode is an interest of interest to us. So the first part of today's talk is going to focus just on SHAREM and providing a foundation for it and some background information. And then we will also dive into some of the newer contributions, in particular leveraging AI. So as you can see in this example, we have something like WinExec on Calc, and that allows us to, if this were a PE file, an executable, we could easily see that enumerated in the item. But if it's shellcode, well, that's much more obscure. It's not immediately clear what that is. So we have something like move EDI and then some particular offset and then call EDI. Well, what is EDI calling? That's not immediately apparent. So there are inherent struggles when trying to do static analysis with shellcode. Now, of course, there are dynamic solutions. For instance, you could use something like WinDebug to address that, but it could be time-consuming and challenging for some people. So SHAREM tries to address that by providing an all-in-one solution that can address many aspects of the shellcode problem, which we'll be talking about in detail. So it really does have some game-changing features. It supports a vast number of Windows APIs, as well as virtually all user-mode Windows syscalls. And we have something called complete code coverage, which is probably not what you think I mean by that, but it's very powerful what it can do. And we also have a virtually flawless disassembler for the shellcode. And there is also a shellcode deobfuscation capability or decoder, so we can do that through brute force methods as well as through emulation. And of course, with all of these, we have support for 32 as well as 64-bit and customizable options via a config file. So let's talk about the SHAREM emulator. So in particular, we are able to support more than 30,000 Windows APIs across 61 DLLs. And so this includes most of the security-relevant Windows APIs that are out there. And if there are others out there that people wish to have supported, just let us know and we can include them. And virtually all user mode Windows syscalls. Sorry if you're looking for kernel mode, we just don't have support for that. And so how it will work is you can take a raw binary hex file, a bin file, or a text ASCII representation and use that as your input, either one, and we can let it emulate and do its thing, extract ILCs, and really gain a wealth of different types of results that we'll be exploring shortly. So it is built upon the Unicorn engine, and all that really does here is just to provide a foundation to emulate the CPU instructions. And so with the high level of details out of the way, we can get a little bit deeper into some of the implementation details of the emulator. So for this to really work with Windows, we need to have Windows structures implemented. So Unicorn is a framework that just gives us the essentials to do just basic emulation of CPU. Your shellcode's not going to get very far with that. It's going to terminate very quickly. So we need to build these appropriate Windows structures like the PEB, the TEB. And so we can do techniques such as the very familiar PEB walking and then We also have WLink module lists and other structures providing the necessary metadata for those DLLs, which are implemented and supported by SHAREM. So now that your shellcode has these structures, it's done the so-called PEB walking, and that takes you to the base address of a DLL. You see the 4D5A, the MZ. And what are you going to find there? We're going to actually find an actual DLL in memory. So we'll actually go and harvest the DLLs from your OS. We do this one time when the program first, the first time you run it, and it's saved for every subsequent time. And it will go and inflate each of them according to a particular algorithm that we created based off of just different P-file attributes. And this is necessary because if we were to not do this, then it would not have the desired effect. So when the OS has these DLLs, it's not the same as the DLL being static on your hard drive. We need to adjust them at certain places so that we can get accurate results. And one thing we have learned about shellcode is sometimes they can do some very strange and interesting things. So it's really best to have the actual DLLs in memory so that we can account for all 100% of those possibilities, which may not be possible if you were to simply simulate it. We'll then use the PE file library to go in there and obtain the runtime address of each of these Windows API functions and then put them into interconnected dictionaries so that if the shellcode tries to go to a particular address, we can just look it up and see what it is. Of course, you might say, well, what about ASLR? Well, this is emulation, so we can simply ignore that aspect of it. So that gets us then into API emulation. So now we can go in there and locate the specific Windows API. So if it tries to go to a particular runtime address, we can log that, we can get the parameters, we can get the runtime address, and so that can give us tremendous insights into what's going on. So right here you see a Metasploit shellcode, and it's pretty clear to see just from the output that it's trying to create a bind socket on an interface over port 8721. So now we can go a little bit into underneath the hood in terms of how this actually works for us during the emulation on API call. So for some, we want to build out specifically what that's going to do. So with virtual alloc, it's going to actually go in there and it's going to check for memory collisions. And if there are none, then inside of the emulation, it will go and actually allocate that particular memory at that particular location. So we're doing more than just simply logging that. And we actually have several hundred of these handcrafted API hooks to allow us to get this type of information in very high fidelity. And of course, we also support Windows syscalls. And until very recently, Windows syscalls and shellcode really wasn't a thing. In fact, we did a lot of research into this, and this actually led to a DEF CON talk and a Hack in the Box Amsterdam talk where we provided a methodology for doing Windows syscalls in shellcode, and even a tool, shellwops. And the reason why was simply because we wanted to make sure that if people were to use Windows syscalls in shellcode, that we would be able to accurately emulate it, because there are some non-obvious aspects to it, especially when you're dealing with WoW64 and 32-bit. So here we have NT allocate virtual memory, and you can specify the exact OS build and get the correct determination of the syscall. So whenever possible, we try to provide what we call smart output. So rather than just having kind of boring hexadecimal values, we'll provide human-readable values. So some of you probably know hex 40 is going to be page execute, read write, but maybe not everybody. And there's a lot that some people simply won't know. So we actually have thousands of these things where we will provide the human-readable form of that. And also, if the Hungarian notation denotes that it's going to be a string or a character, then we will go and parse the string and provide that as the output rather than just simply the parameter. So it's very efficient in presenting the information in a way that is more comfortable to actual humans. So in terms of the artifacts, we provide quite a lot of artifacts. We provide them in a number of different categories. In this case here, we can see some correlations. So you have a file that's being downloaded, but it's being renamed. And actually, the tool can even go and try to download live files for some of them. And if that is the case, it can actually do an MD5 hash of that and determine specifically what file that is. If the file resource is gone, no problem. We'll simply simulate success so that the shellcode does not terminate prematurely. We also have a pseudo file system, so you can see exact places on the file system where it may be saved, and really just a wealth of other categories that we can't really get into in the interest of time. Additionally, we will display structures. So in this particular case, the Windows API has a couple structures, and we're actually seeing those structures rather than simply a pointer to the structure. So that can be significantly more meaningful. And these are all handcrafted. They take a little bit of effort to create them. So we don't have them for 100% of structures because there are quite a number of structures out there. And even structures within structures. Yes, a nested structure. So we have 3 structures, including 2 that are nested inside, and we're able to see all of those. We also provide a Windows registry manager, which allows us to record registry actions in a very great amount of detail, so we can keep track of things like if things are being added or modified, and even identify certain modder techniques like persistence or credentials without the use of AI. And of course, handles. So we can use handles to register keys. So instead of displaying a hexadecimal value, which should be the correct thing, we will then instead display the key, the registry key that corresponds to, which is, I think, much more user-friendly than just providing the hex. For Windows syscalls that deal with the registry, we can also account for those as well. And so in this case, we see that the person's obviously trying to do some persistence there. And we also have the familiar p-object attribute structure, which is very persistent across, or very common in a lot of Windows syscalls. That is one that we do support. So another feature we have is timeless debugging, where we can log different CPU instructions, the register values both before and after. And you have a number of different options there. And it'll produce it as an emulation log.txt file. It's maybe not the best way to do it, but we do get the information there. And so if you want to go review what happened over the course of a Windows shellcode, then you absolutely can do that and maybe figure out why something behaved in a certain way or not. And one new addition is also adding a stack log. So this is a separate emulation log, and this one does take more computing resources. So if you do the stack log, it will slow you down. And this one runs in addition to the other one, but here we can actually have a snapshot of memory so you can see things that are added to the stack. So we have a value 6D moved into DL. We push that onto the stack, and lo and behold, we see it there in the stack at its proper location. We also efficiently have a handle manager and a memory management system, so we can keep track of handles that belong to different things like registry keys, as we mentioned, or pointers to DLL-based addresses. And the memory manager will deal with things like collisions to make sure that we don't have the collisions and to allow them to be, the allocations to occur in a very smooth fashion. So we could take a look here at an example of handles. And so in this case, we have LDR load DLL. And we see that there is a pointer to a handle, and we are able to then see the specific library that's being loaded by that. As part of our research, we looked at a lot of public repositories of shellcode, and additionally, we ran a lot of malware and things like Cape Sandbox and tried to analyze memory looking for shellcode, and we found predominantly most Windows shellcode is 32-bit, but there is some 64-bit out there, and so of course we do provide support for them. We want to do that absolutely. So let's talk about complete code coverage. And so this is one of the most groundbreaking aspects of the tool, and what we mean by this is you have code that is completely unreachable for whatever reason. Can we reach it? Well, with this, we can. We absolutely can. So we will log, we ensure that all code paths are traversed and are emulated, and so we can capture functionality that otherwise wouldn't be there. So we've added a lot of new particular features and options that you, the user, can select that weren't there previously. Some background information on the complete code coverage. So it was inspired by AFL, so that with this we can log or record all control flow paths, both taken and not taken. And at each time there's a place for convergence where you could go left or you can go right. We're going to take a snapshot, if need be, so we could capture the CPU register state and additionally a snapshot of memory. And so if the shellcode needs to restart, that hasn't been visited, well, we can restore that and then go and revisit it. And so we've taken some feedback from VB in the past with regards to complete code coverage, and we have greatly improved the speed and functionality, added some additional capabilities. For one thing, we reduced the snapshot size so that it's not the entire memory, but just a smaller amount. That was a big performance boost. And we also can track call instructions for possible code execution, and you can exclude specific ones. If you know they're going to be problematic, you can place them in a special JSON so that it will be excluded. We also have visual cues, so you can distinguish between those that are executed and non-executed, and a lot of options in the config file that you can address. And finally, it can also accurately handle jump tables. So more or less, most situations where code coverage would come into play, SHAREM should be able to address it with some of these improvements and enhancements. So here's an example. So we have complete code coverage without. And the one on the left is how it should be. This should only work on one specific machine. It's looking for a particular computer name. And so normally it would terminate, but with complete code coverage, we actually are able to restart it, and we're going to go back and rerun that at that spot, take that path that we should not have taken, and we are able to actually have that WinAPI, that registry key value being set. So with this, we can really discover a lot of functionality that otherwise may not be discoverable. So let's talk about encoded shellcode. So with the tool, we can use SSDeep to address self-modifying code. We can see that it has changed, and with that, I won't get into all the details in the interest of time, but we will get the decoded form and send that to our disassembler. That's what we will see. And so it's really kind of a hybrid of static analysis and in some ways dynamic if you consider emulation is dynamic. And so even though this is fully encoded, we see it as if it were not, and we have all of our APIs identified alongside the different parameters. Same thing in IDAPRO, and we have really just a series of unknown bytes, mystery bytes. So some of the new aspects of the talk, other than complete code coverage here, is leveraging AI to enhance shellcode analysis. And so how this is going to work is it works with OpenAI. So if you have a key to that, you'll need to supply a key and the config file. And SHAREM already provides a wealth of phenomenal, extraordinary amount of details on SHAREM. And so we basically feed that into the AI and allow it to perform some analysis for us. So the first thing it does is it'll try to identify a specific MITRE attack technique. So we look at the totality of all the Windows APIs, all the syscalls, all the strings, all the artifacts, and figure out big picture what is going on. So a typical shellcode, you might have 2, 3, 4 different MITRE attack techniques being identified. And we will see a detailed description of it as it pertains to the actual shellcode itself, not a generic thing, but we're getting specific details from the shellcode. And we get the appearances where it appears, so you can go back and check it out if you want to. In this case here, we see that URL download to file A is being tied to bits jobs, and we have create process being used to execute commands via Windows command shell, the specific MITRE techniques, and deletion is occurring to hide some evidence. And we get the specific details that are laid out in front of us. Here we have other things, registry manipulation, system information harvesting, clipboard data interception. And again, the specific details are there for us to analyze, and we can go back and find the exact place and the code. Another example here, we have some more clipboard data interception and registry manipulation. It will also try to identify the most critical technique. So again, there will be multiple techniques unless it's a very trivial or trivially simple example. And so which is the most critical that we need to maybe pay the most attention to? It'll give us that information, or at least try to. The MITRE attacks technique summary will look at all of the different techniques and then try to boil that down to kind of a high-level summary and providing specific details from the shellcode along with specific MITRE techniques. So if we just wanted a nice overview of what's going on, then we have that readily available. So I thought, what else could we do with this? I thought, well, why don't we try to correlate that with Windows APIs and how they pertain to MITRE, the MITRE attack technique. So the first thing it will do is it'll provide a definition, and the definition is pretty obvious. You could get that from multiple sources. But what we really care about is the usage, and that's going to specifically deal with the malicious usage of the API, and hopefully as it pertains to MITRE. Now, not every API may necessarily be associated with MITRE, but a lot of them may be. And so we get the specific detail usages with them. So in this case here, we have get computer name and a set key value A, and we're seeing, again, the specific techniques and details there. So we have sleep here. We have sleep for 3,000 milliseconds, and we're being told that it could be used to evade detection or to wait for another process that can complete. And with delete file A, we see that a specific file is being deleted and the different technique that aligns with. And of course, we made a big emphasis on Windows syscalls, and so we support that as well. And it knows to recognize if it encounters a Windows syscall that this is something that's kind of special and unusual, and it will probably want to draw attention to that fact. But we provide the same usage information for that as well. And then the executive summary is MITRE agnostic, because what if MITRE doesn't address something? So we can look at everything that's going on that's malicious in nature and try to provide a clear, kind of concise summary of all of that, so you can read through that and know what this shellcode is actually doing. So that's something that could be, I think, very impactful and useful to somebody who just wanted to have a big picture of what's going on with the shellcode. So artifact summary, we'll look at all of our different artifacts. We'll have a lot of them, and I'll analyze them and try to create a nice, user-friendly, concise summary so we can enjoy that. And then the next section, which has nothing to do with MITRE, is the overview of the disassembly and data. So we can look at things like, look at the actual disassembly, what's going on, what APIs are being used, and then the data. Data could be things like strings or checksums. So the overview gives us kind of just a very brief introduction, and also it may discuss things like just simple shellcode mechanics. Why is this shellcode doing this? It's just simply trying to resolve an API runtime address. Shellcodes typically put a lot of work into doing something like that. This is something rather unique. I haven't seen this anywhere else. I think it'd be very impactful potentially is this usage of AI. So we have strings and data, and so we can have the actual string itself, which is the example, and then the description, for instance, string for DLL name, and then you have the possible malicious usage. And so for each and every string, it gives us some insights into how this could be used maliciously. So used to download a potential malicious executable, path where a downloaded executable is potentially saved. So if we weren't able to recognize this, and I think most people in this room probably will recognize a lot of these, but if somebody were new to this, then this could be very useful. Used to disable security defenses. We have a couple of those there. In this case, we have registry path for persistence is the description, and then is the possible malicious usage. If you didn't know what that meant, it tells you, in other words, used to ensure the malware runs at system startup. So a lot of people would probably recognize that particular string, but if you didn't, then you gain some insights with that. A couple more, we have exfiltration and modifying some system settings for terminal server connections. Again, if we didn't know the possible meaning of the string. And then other comments can just be other little things that the AI thinks may be of interest that wasn't already covered. So in this case, we see that it speculates what may be done with Connect, the Connect Windows API. And then also I thought, well, why don't we try to look at the function names? Because shellcode can be very complex. Shellcode can have multiple functions. Could we suggest some names if you wanted to go in there and rename them? So it will analyze what goes on and gives you these, so you could use that if you want. So let's move on to the disassembler. And so When I started this project, I looked at something like IDAPRO or Ghidra, and it'd be like 60% accurate because it would do things like misinterpret data or strings as instructions. That's not accurate. And you start disassembling it at incorrect offsets. And so it was just a mess. And so I developed different analysis phases to address this. I would compare original source code that I had in assembly, try to figure out the root problem, and then address that with the different analysis phases so that we would get better results for everything, not just for one sample. So the end result is it seemed to be very, very effective, definite, huge improvement. And so we can identify, we can integrate emulation data so we can identify the APIs and the shellcode. This is something that IDAPRO or Ghidra can't do. And provide also disassembly annotations like different PEV features, API pointers. So these will be generic areas that will be updated with the runtime address of the shellcode once it resolves those APIs, and then it can reference them. And so we can look at IDAPRO to the left, and unfortunately IDAPRO is not really capable of determining the APIs that are being called, and that's to be expected. That's not something that a traditional disassembler can do, but SHAREM can actually do that, and so we can have those being identified. And we can also identify strings, and those will be labeled correctly as data. If it's something like a push stack string, we'll have a comment because it's not a string, it's an instruction. We're pushing those, the ASCII onto the stack. And then don't have time to go into the details for this, but we'll actually, in a very clever way, integrate the emulation data to improve the disassembly, because we know where the shellcode, or where instructions begin and where it ends, and so we can use that to override what possibly could be inaccurate. So the end result is the shellcode should be, the disassembly should be more or less virtually flawless. So here's an example of distinguishing between data and instructions. On top, we have actual instructions. We have a call, and we have that call identified to the Windows API. And then we have a return. And then down below, we have data, and the data is displayed correctly. It's not being misinterpreted as instructions. We have checksums. We have API pointers. We have strings. So here's an example of a decoded shellcode, and of course it's fully encoded, but we're able to see that as if it were fully decoded. Again, it's kind of a hybrid of static analysis and dynamic, if you were to count emulation as such. So let's talk briefly about the Ghidra SHAREM plugin. So this was developed by Max Kirsten of Trellix. He did this 100% on his own, had no involvement. And so you can deploy that in Ghidra, use their script manager, and what you will do is you'll run SHAREM headless. So you can run it outside of the GUI. There's an option, the config, and you can then use SHAREM to integrate it into Ghidra. So this is the before. You can see decompile. We have some different functions there. And then after, we're able to then go and integrate the SHAREM results. So we have the APIs identified, the parameters. It's a big, big difference. And then, of course, with data, we can have the data being handled correctly in Ghidra, and some more data as well. And if something were encoded and SHAREM is able to deobfuscate that, the same thing is going to happen in Ghidra. We'll have the deobfuscated shellcode being presented in Ghidra in that fashion. So if you want to download that, you'll need to go to the Trellix GitHub to get that. So we're getting close to the end here. So reporting, we report on things in extraordinary amount of detail, lots and lots of different hashes, lots of different data points, probably more than you would expect it would be possible with a shellcode. And they can even handle and analyze PE files. And it can determine definitively, or hopefully definitively, whether or not a shellcode or binary is shellcode or it's just random memory. So we produce a number of different outputs, so ASCII text representation of the code, the raw binary. If it were decoded, we would get the raw body, the part that has been decoded by the decoder stub, text output, a JSON, so you could use that JSON in various other projects. The AI stuff, that also produces a JSON, one big JSON, which is also displayed as text. A C tester, so you can, if you have something you want to launch, something like a WinDebug, we've had that since day one, you can compile that and then debug that in that type of tool, and then prints to the screen. So I'd like to thank you, encourage you to go and download it. If you like this project, you think you might, then give it a star or share it on social media, let other people learn about the tool. And I would also like to acknowledge the funding agency